Thanks. Okay, can people hear me? Let me get chat pulled up. Hello. All right. Okay, so today is recursion day. All right, and yeah, the lesson plan says induction and recursion, but I think that's kind of redundant because at least for the AMI, like a lot of the induction that you will see is just basically recursion, just like framed kind of nicely. So yeah, we're gonna have a bunch of recursion problems, and it's a more or less blend of algebraic and combinatoric, which is when they occur. I have 7 problems here, but they're all like AMI problems, so I'm not sure if we'll be able to get through all of them. But when will the handouts come out? Later. So let's get started. Let's do a nice warm up. Problem 1 right here. If you have paper, I encourage you to just write down the essential parts. All right, and just think about it. The theory, we'll just introduce it as we go along. I think the problems more or less guide the main ideas. This can also be seen as a continuation of sequences and series, though I think this covers the more trick-related stuff. For the n-1 is part of the subscript. You can see that it's slightly smaller than the normal size text. Okay, so I'm gonna go ahead and, oh, perfect. Transitions might be really easy today. Okay, so let me just rewrite the main functions, and they were a of n is equal to a of n-1 plus. All right, so to the people who like tried to solve this, what was the first thing that you did? List out a few terms. That's exactly what I was hoping for. Great, because yeah, that's how you get intuition for a problem. And there are a lot of cases for lots of cases for when like the recursion is just really, really horrible, and you just list out a few terms and it magically loops. I think a good example of that is this year's AOIME, I think problem like 5 or 6. So let's try and like list out some terms. So can anybody tell me the first few terms of the A sub n's? Because the computations everybody here can do. So we know that A sub n goes like 1, 1. Again, next few terms are 2, 6, 24, 120. And that should be a 120. And I believe this is correct. So does anybody see a pattern with this? A lot of people are saying factorials, and yeah, that's exactly what this is. So this is an AMI, which means that we don't have to prove anything, which means that we can just do whatever we want with this. So we might guess that a sub n, I think, is equal to n factorial, because the terms start at 0, so you have to be careful. Yeah. Once we're done with this, I'll give a brief proof for why it's true. But okay, what about the B events? What are the first few terms of this? We have 1, 3, 12, is it? 60, 360. Can anybody find a pattern with this? And I'm gonna just wait for a minute so that people can just stare at it, try and think. Oh, I see. That's people are looking at these ratios, and you go 3, 4, 5, 6, and this also reminds us of factorials. Yeah, that's really cool. So if we look at this, we can see that these are actually half of different factorials. So if we assume this pattern continues, and again, we're assuming it continues, we get that b of n is equal to n plus 2 factorial over 2. All right, and we have to be careful. Like, it's always a good idea to just check this for like a few numbers just to see that they work out. Indexing can be a bit difficult sometimes, and you never want to underestimate that. So let's just assume this works. So then b sub n over a sub n is going to be n plus 1 times n plus 2 over 2. And does anybody not see what I did here, where I just wrote n plus 2 factorial as n plus 2 times n plus 1 times n factorial? I did not forget the n factorial because I divided by it. So it cancels out a lot of the terms. So we're actually almost done because we want b32 over a sub 32. So this is going to be 33 times 34 over 2. And I'm told this is equal to 561. And that is correct. Does anybody have any questions about this? What Amy is this? I forgot to put down the source, but this was actually a question 6. I think the forum consensus was that this was one of the easiest questions on the test. How we came up with the rule for B of n, we just looked at the pattern and guessed. Like you see, like times 3, times 4, times 5, times 6. Where did I get n equals 32? The problem asked for it. All right, and I am not able to show the problem up here, so that is my bad. How we can come up with the rule, that's a great question. The trick here is to notice that we can divide by a sub n minus 1. So this rule becomes this. And what this means is that the ratio between two terms increases by 1 each time. And that's what explains the factorial structure. So since you can think of this, since a sub 0 over a sub 1 is 1, we know that we're going to have to multiply by 2 next, then by 3 next. Everything is encoded a lot more clearly when you look at it like this. And this way of like proving why we get factorials is also something that you should look out for, just manipulating this expression to make it a bit more understandable. All right, if there are any other questions, please address them to Andrew. I will continue. Next question. This one's a mouthful, so definitely read it for a bit. Now that I look at it, it isn't as much recursion, but it's still decent practice. All right, if anybody still wants to read the question or like record the necessary information, let me know right now. They actually alternate between geometric and arithmetic progression. That's what makes it tricky. Yeah, so you can see A1, A2, A3 are arithmetic. A2, A3, A4 are arithmetic. Sorry, the A1, A2, A3 is geometric. Then A3, A4, A5 is geometric. A4, A5, A6 is arithmetic. A5, A6, A7 is geometric. All right, I'll wait another minute if people still want to read. All right, I'm gonna have to go because there are a lot of problems towards the end that I want to cover. So, whiteboard. I'm gonna write it out. I'm gonna try and write out everything. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this is Firefox. And hopefully we don't need too many more. So arithmetic, or no, this is geometric, this is arithmetic, this is geometric, this is arithmetic, and so on. All right, so this is, let's say this is 1, and we don't know anything about the second term, so this is x. What is this third term right here? And it is x squared. And why is it x squared? Because these three are in geometric progression. All right, what is this next term right here? All right, I see 2x squared minus x, and it's gonna look like this is gonna be a lot more space. All right, how about this next term? All right, and isn't, I don't think anybody has gotten it yet. Or, oh, is that really true? Why is it 2x squared minus x? Because these three have to be in arithmetic progression. So the next ones also have to be in geometric progression. So the ratio should be what? 2x squared minus x over x squared, which is 2x minus 1 over x. So it is something nice. I'm going to start by writing this out. Whoops. All right, and this is terms 1, 2, 3, 4, 5. So we're halfway done. Nice. So can anybody tell me what the next term is? All right, you see where we're going with this? All right, and we see that we have this factor, so we can write it like 3x minus 2 for 2x minus 1. All right, so now a lot of people are getting tripped up already because you have to remember that we have to switch to a arithmetic sequence this time. So again, geometric, arithmetic, geometric here, arithmetic here. And I am starting to see a pattern with this. So I'm glad. because it seems like when we do the geometric over here, all right, we go from here, we multiply by 3x minus 2 over 2x minus 1. So we continue again, we get 3x minus 2 squared. And I do think this is correct. Yeah. So then the next one, if you do the math, hopefully you're starting to see a pattern. For x minus 3, this is quite nice, I have to say. So you can see that we have the structure of like, we have a square, then we have this term, then we have another square. And then what is this? Oh, is this the 9th term? And then we have the 9th and 10th term right here. Great. So we just add these two up and we can factor. That's what makes this nice. 4x minus 3 times 9x minus 7 is going to be equal to 646. And let's just count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. All right, so the way that I got these terms was just basically just going along the line. And now you could do this and you could solve a quadratic for x, but that's really inconvenient. So another option is you can find two factors of 646 and guess and check. And the reason that guess and check is like actually feasible is that we're given that x is a positive integer. So maybe we can do this. So we look for factors that are somewhat within these ratios. So I have been graciously provided 19 times 34 by the chat, and this seems to work. But evidently not. Yeah, we could plug this in. Like these like look relatively close, but we solve here, we get x equals 5. We solve here, we do not get x equals 5. Or no, neither of them get a solution. Whoops. So instead, I think a better choice is 17 times 38. Yeah, and when we solve these, we get x equals 5. All right, what I did is, what you could have done is just literally go through every single possible factor pair of this. There are only 4 of them, so it's not that long. And then you solve this, x equals 5. You solve this, x equals 5. Nice. So the next term here is going to be, of course, 5x minus 4 squared. Is there a way to do it without writing it all out? After you write out these terms, you can start to see a pattern. All right, and when we plug this in, this gives us 441, which is 21 squared. So that's not quite what we want. So we have another term here. Then we have 6x minus 5 squared. Then we have another term. Then we have 7x minus 6 squared. All right, and this is what's getting close. Oh, okay. What we want to calculate is the greatest term that is less than 1,000. So I'm just like skipping the irrelevant terms here. And from this point, what you could do is you could just like plug this in and just like actually like bash every single thing, but it's cleaner to keep it in variables. All right, so the pattern. So you can see that every other term is just like 2x minus 1 squared, 3x minus 2, 4x minus 3, 5x minus 4, 6x minus 5, 7x minus 6. And then in the middle, we just take the product of two consecutive terms, take the square root. So it's sort of like we're like borrowing factors from each other. I'm told that the next term is the correct one, but I'd like to check. All right, when we plug this in, 29 squared is 841, which is definitely high up. The next term is 7x minus 6 times 8x minus 7. So that's going to be 29 times 33. All right, that's 957, I believe. And just a quick tidbit, the way that I did this was I did 31 squared minus 2 squared. which is really nice. So yeah, that's it. We're done. So the thing here, again, is like we just read out a few terms and we found a pattern. All right, if you have any questions, again, consult Andrew. So, oops, there we go. Can everybody, oh no. What do I have my squares memorized to? I think about 30-ish is where it starts to taper off. If you wanted to, you could prove it, yes. And that would be an inductive argument, but you're not going to do that on the AME. All right, so now we have an AMC problem. This one's, I'm actually going to skip this. I think I will not have time for the other problems and I want to get to the other ones. This is a good exercise though. So let's just go to an AME question. I didn't answer question 1.2. I'm pretty sure I did. 957, which is pretty darn close to 1,000, thinking about it. Oh, I see. They wanted 957 plus n. Well, okay. Oh well. It's a different number. Yeah, I apologize. Let me show what I'm being scolded for. They wanted this number, not just a of n. But if you kept track of the term, it would be easy. And the answer is 973. Okay, thank you for that. But the important part was like figuring out the control over the sequence and like you just extending that. All right, so this recursion is simple enough. So yeah, I'm going to present a solution that's I just found, and it's different from everything on the forums. I quite like it. All right, and this is a question. This is a problem 14, and problem 14s have this reputation of being like easier than like expected, but this one is definitely requires a bit of insights. So A1 equals 3, A2 equals 3. Wait, can I go? What do you want me to go back to? The problem? I'm writing it right now. And we want the floor of this monster. All right, so there's no way. Okay, so for this one, there's no way that we're going to get this by writing out all the terms. Fourth term gets pretty large, and they're only going to get bigger from there. So we're probably going to have to do some manipulation with this, all right? And there's no point in writing out terms, especially when we're like having to do some approximation. So let's take a look at this. All right, is there anything that we could do with this? All right, I do have a suggestion from the chat. Maybe we could isolate a sub n plus 1. All right, and this is appealing because this is like how we would do it if we're like doing values, but it turns out that this actually doesn't help us much because we're not trying to find individual values. All right, but let's take a look at this expression. Is there a different way that we can rewrite it? Because it looks weird, that maybe there's some structure behind it. I have a lot of interesting ideas, but the one that motivated this solution was writing it like, Yeah, we're splitting it into two different fractions. So A 2006, or let me keep it in order. Expressions of the form like x over y plus y over x have occurred enough to the fact where like I remember them. And maybe splitting them apart like this might be the key. So what this tells us is that we're going to want expressions like this and expressions like this. Yeah, they're reciprocals of each other. So what can we do? And here's the trick. This trick is really similar to the first question that we encountered, in fact. So we're going to take this expression and we're going to actually divide it by a sub n. And look at what we have here. Do the reciprocal addition trick. What is the reciprocal addition trick? And look, these are exactly the expressions that we have here. So maybe we can express this as a recursion. The problem with this is that I don't want to take the reciprocal of this right-hand expression. That looks nasty. So I got from here to here by dividing by something. I divided like overall by a sub n minus 1 times a sub n. And now what I'm trying to ask is there a different expression that I could divide by that maybe gets me something symmetric, but different? All right, and this is something that's, when I was solving this today, I really liked. So what I'm gonna do is, instead of solving for a sub n plus 1 here, I'm gonna solve for a sub n minus 1. Yeah. So what I'm gonna do is I'm gonna do the same thing as before, except I'm dividing this expression by a sub n plus 1. So what do I get? This should be a plus 1. And I'll keep them in, I'll put them in order. All right, does anybody confused as to how I got this expression or the first expression for that matter? What is the intuition behind dividing by a sub n? Great question. I wanted to make something that looked like this, and I had originally written it like this, and I was like, ooh, this looks close. I just need to divide by an additional a sub n. So that's how I got to here, and look, it appears twice. So I guess writing it in standard form was a great first step. And then I thought, ooh, I could do it the other way too. That's how I got here. All right, I'm assuming that everybody's clear on how I got this. What could I do with these? How did I get to the last one? I divided by a sub n plus 1 times a sub n from the original one. All right, what can I do with these expressions to maybe make them look a bit like this? Substitution will not help us now because unfortunately we are not in the realms where we can translate these numbers great. But we can, yeah, we can subtract these two equations and do a bit of rearranging. So this is what we end up with. And I'm going to go ahead and define another sequence. B sub n is equal to a sub n plus 1 over a sub n plus a sub n over a sub n plus 1. So I'm going to use good practices, and I'm going to say what we want. Want b sub 2000 and what? 2006. Yeah, we have to make sure that these expressions match up. And it's very easy that I could trick myself into thinking we actually want b sub 2007. And maybe that might cause issues. So what we do is we subtract, and we end up getting the following. You can work through the addition yourself. And I think at this point, I tried to do some fancy dividing thing, and nothing worked. And I was staring at this for a really long time. I defined b sub n over here. It's just so I don't have to tire my hand out writing this. But I wrote this in a very specific way, so that suggests a very specific trick. Can anybody think of what that trick could be? I'm looking for a word. Has 3 or 4 syllables. Telescoping, great, yes. So hopefully everybody's okay with this. I'm going to erase it. All right, this is the main recursion, but I think we actually do not need that anymore. Yeah, we're gonna telescope this. And why does telescoping work? So let's just write this out. All right, b sub 2006 minus b sub 2005 is going to be 2007 over a sub 2005 a sub 2006 minus 2007 over a sub 2006 a sub 2007. All right, so now what happens if I write this? And it looks like my fractions are gonna. My indices are a bit hard to read, but you can see that these cancel. And these cancel. All right, we can keep going. And we get to all the way down to b sub 2 minus b sub 1. We stop at 1 because that's the first term that's defined. Over a sub 1, a sub 2 minus 2007 over a sub 2, a sub 3. And we just continue these lines like that, and we continue these lines like that. How long did it take me to get this problem? I think 20, maybe 10, 20, 30 minutes. I don't really know. I wasn't typing. So once we add up every single one of these equations, we get b sub 2006 minus b sub 1 is equal to 2007 over a1, a2 minus 2007 over a 2006. And I think we're so close to being done. This is our magic equation. Because let's figure out, oh, what is b sub 1? B sub 1 is 2, because we can just plug these in. So b sub 2006 minus 2 is going to be equal to, and what is a1 and a2? Those are 9, so I think this adds up to 223. And we have this final term, but what can we say about this term? What, it turns out that we can actually ignore it. And that's because you remember how the sequence got really big really fast? And because of this, we know that this term is just going to be really, really close to 0, but it's still going to be a bit positive. So I'm going to write that as minus epsilon. All right, 223 minus a ridiculously small number. So we know that our answer, B sub 2006, is 225 minus epsilon. And yeah, it doesn't matter because we want the floor of this. So our answer is 224, the greatest integer less than that expression. All right, just as a general case, when it asks for like the largest integer less than or equal to, and it's like a really high level problem, most of the time it means we're probably going to like subtract or add like a really small term like this. So let's think, how did we solve this? All right, what we did is we just took the expression, we played around, we saw that we could split it up like this, and we figured out how could I get these terms. We did it in like 2 different ways. We added them, and once we rearranged, it was this really nice cancellation. This was a problem 14. I think it more than deserves its place. Because I could, like, it took me not that long to solve it, but I think I got lucky. I could see a lot of people spending a really long time on this because it's hard. Yeah, lots of moving parts. So that's the pinnacle of all the algebraic ones we're gonna do today. So now we're gonna move on to a different skill, and I'll only be able to. Yeah, I will only be able to like maybe present a couple of them because I have to leave like right at 4, but I'll try and do as much as I can. So yeah, let's move on. This is a slightly different skill set. All right, and let me just take a look. I'm just gonna jump straight to the Amy problems. So yes, so recursions, combinatorial recursions, like can come up when we're thinking about sequences. And I'm gonna take this one super safe because it is really easy to set this up incorrectly. So just think about it for a bit. I get a question. Is this related to the Fibonacci sequence? Maybe, sort of. Like, it's only related in the fact that it has recursion. But it's definitely a tricky one. Casework on A? What does this casework on A mean? And keep in mind that we are not going to use casework or as much casework because we're using recursion. So the way that I'm going to set it up might not be the only way, and you guys might thinking, let's clear this. All right, and how are we going to do this? All right, so examples, like let's take a look at all the smallest sequences that work. All right, B, A, B, A, B. So the standard way of thinking about this is how many blocks can we have of like 1 by 1 or 1 by 2 that fill up a certain row. And the way that what we usually do to solve this recursion, this is the Fibonacci one, is like, let's say a sub n is the number of ways to tile a strip of 1 by n with these blocks. This is 2008 Amy 1. All right, I will write down the condition. A runs are even, B runs are odd. So yeah. And in this case, what we do is we say, oh, what if the last block is a 1 by 1? then the number of ways to title the rest is a sub n minus 1. What if this last block is a 1 by 2? Then there are a sub n minus 2 ways. And this is how we get the Fibonacci sequence. So let's think about casework on something similar. I'm doing a different problem. I probably shouldn't have digressed into this. It will be clear. Oh, another valid sequence. B, A, A, B. Nice find. And A, 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 A. So let's say we have a sequence of n letters. All right. This is the length 14. Oh, I was just demonstrating the basic Fibonacci one, but that was a tangent. Let's get back on the course. So what we could do casework on is if this letter is B or A. But there's a problem with that. And that problem is we don't know anything about this. Like, for example, we have this valid sequence, B, A, B. But when we tack on another B here, it's no longer valid. So yeah, it messes with the even odd. So the way that we're going to have to solve this is be a bit more restrictive. So we know that this can end with rely on a sub n minus 2. All right, but it turns out that that could fail using similar logic. But you can definitely try it for yourself to see why. So what we're going to do is we're going to get a bit more specific. All right, a sub n. We're going to define as number sequences that end with A. And then B sub n. Number sequences that end with B. Yeah. So this is how we're going to set up our recursion. And yeah. So the reason that I do this is that it completely takes care of this following thing. Let's now do casework on, let's now figure out a recursion for a sub n. All right. A sub n is equal to. So how many ways can we end with a's? Well, let's say we end with 2 different a's. That's b sub n minus 2. So let's say we end with a, and we know that this is going to be something that ends with the b. Oh, great point. We want a sub n plus b sub n. All right, because, okay, yes, so how many ways can we end with an a? We can have 2 a's, we can have 4 a's, but we know that this like remaining chunk has to end with a b. And then I'm going to leave this at plus dot 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 because I don't know what goes at the end. Could be a 1, it could be a 0. It's unclear. So now we have this equation. And I'll leave this as an exercise for like how I got this. But we do a similar thing. Actually, I'll just explain it. We can end with 1b. And then the rest of it has to be a sequence that ends with a. We could also end with 3b's, 5b's, and so on. So I have these 2 recursions now. Why are we summing the recursion? That's just how it comes up naturally, because these are different cases. All right, we're looking at cases that's where A is at the end, and we think how many A's are there? And we're looking at cases where B is the end, and we think how many B's are there? Yeah, these are going to be mutually exclusive. That's why this works. Every sequence will end with A or B and not both. So one nice thing that we can do with this is sort of similar to the previous one, and we could use parallel structure. All right, look at this. So you see how B's have a lot of the same terms? And what that means is that we can cancel them out. So A sub n is actually going to be equal to b sub n minus 2 plus a sub n minus 2. Yeah, and this is like cool when you see a lot of these similar problems. All right, but b sub n, if you do the same thing, is going to be a sub n minus 1 plus b sub n minus 2. So now we have these recursions, and maybe we could try and combine them in a smart way, but nah, I think what I want to do is I might not have time to demonstrate the next problem, so we're just going to go on with this. But just recap for what we've done so far. We've written the answer in terms of these a sub n's and these b sub n's, where we have sequences that end with a or b, and we've written recursions based off them, just doing casework on how many of the a's or b's they can end with. So we get these recursions. And oh, I should not have erased that. Yeah. So we can use this. I will actually erase everything else. That should be an a n minus 2 over there. That got cut off. Because we need to use these to get initial terms. So what I'm actually going to do is I'm going to write out every single term. This definitely should be a plus. Because you could think of it like substitution. All right, so what is a sub 1? How many sequences of length 1 end with a? And the answer is 0. And this corresponding thing must be 1. All right, how many of length 1? Of length 2? That should be a 1 and a 0. And I'm going to fill these in, and then we're going to use these to check that our recursion is correct. The number of sequences of length 3 is 1 and 2, I think. So let's check this. A sub 3 is b sub 1 plus a sub 1. That looks to be correct. This is a sub 2 plus b sub 1, which is also correct. Okay, cool. So yeah, what we're going to do is we're going to carry these throughout the entire table. Is it not 2 for b sub n? Why not? I think it should be 1 and 2. I am quite positive this is correct, but if not, then it's a silly way to get it wrong and not what I kind of want to teach right now. Okay, so yeah, we're just going to continue this. A sub 4, b sub 2 plus a sub 2, so this is going to be 1. All right, and b sub n. B sub 4 is going to be a sub 3 plus b sub 0, so this is also 1. Yeah, I think these are the only two that work. So we're just going to continue. This is 3. This is 3. I've written everything here. I think this is all encompassing. So you can check with this. So this is 3 and this is 3. 1 plus 2. And yeah, so this is going to be 4. This is going to be 2. And no, it's fine. Most of the times when people challenge me, I'm the one that's wrong. So yeah, and we're going to have to be really careful that we don't mess this up. So it's always good to just check. 2 is 1 plus 1. 4 is 3 plus 1. All right, 6 is 3 plus 3. 5 is 2 plus 3. B sub n is the number of sequences ending with b. Yeah? All right, I'm going to keep going while you keep formulating your arguments. All right, 6 is 2 plus 4. 10 is 6 plus 4. 11 is 6 plus 5, and 11 is also 6 plus 5. Huh, this is interesting. 16 is 6 plus 10. 21 is 10 plus 11. 22 is 11 plus 11, 27. And now, yeah, you can see it's getting big fast. This is going to be 37, 43. And let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So only 2 more. 22 plus 27. 49. 37 plus 27. That's 64. All right, 37 plus 43 is 80. 49 plus 43 is 92. We add these at the bottom because remember, we want A sub n plus B sub n. 2 cases for B sub n would work for length 3. Yeah, that's why I have a 2 right here. Remember, we wanted A sub 14 plus B sub 14. The handouts will be released later. That is all I am able to say at the moment. Okay, any questions about this? There's probably another way about looking at cases, but this demonstrates recursion quite nicely. But yeah, so what we did is we literally just wrote out every single possible value because we could try solving this, but usually that's not fruitful. Not unless it's like really obvious what the solution is. All right, I do not have much time left. So what I'm gonna have to do is I'm gonna show you the last problem and then outline how to solve it. Because this is a pretty epic solution. Just a sketch. Yeah. If I have enough time, I might just like try and fill out the table really quickly, but yeah, this one is quite interesting. Yeah. Yeah, so you see, like an important part of the last problem is that we like had to like do a lot of computations and write out a lot of values. But we knew that it wouldn't take too long because the numbers were small for most of it, and we knew that we only had to go up to 14. We're gonna have to do something similar here. So yeah, I will draw out the diagram for this. I'm going to share the whiteboard again one last time. So and yeah, we're going to try and position this in a clear way. So we have a heptagon. So you all get to laugh at my bad heptagon drawing skills. All right, so S, P1, P2, P3, E, P4, P5. Was there any recursion in 2020, Amy? I don't know. I don't remember. All right, so we start here. And the frog is just going to jump left to right. And once we reach vertex E, so if we go like 1, 2, 3, it stays there. So we want number of paths of length. I'd switch to lowercase. At most 12. And this is sort of recursion. So for example, this really short path of 3 hops, that would work. This path of 4 hops that goes the other way would also work. So what I'm going to do is we are going to compute every single possible path. So S, P1, P2, P3. And this actually might not work. This might not work really well given the small space I have, but on paper, it's so much easier. S, P1. And I'm writing S at the top and bottom. These are exactly the same, but it's convenience to do so. And these numbers are going to get big fast. All right, so we're going to do recursion based off every single path and where they end, like all the possibilities at the end. So this is like, think of this as this massive overkill. So let's say we start at S. All right. After, there are two different possible paths, one that ends at P1 and one that ends at P5. So no other place works. So let's take a look. All right, how many paths can lead to S? So S can like receive things from P1 or P5. So we can say, we can write this equation. This is not, I'm going to put this in quotation marks because this is really bad notation, but it gets the job done. Because at time 1, S, or at time 2, like the number of ways to get to a path to S can occur in two different possibilities. It can come from P1 at time 1, or it can come from P5 at time 1. So S is actually going to be equal to 2. And we can check this. There are two ways to get from here to here. I suspect I might be losing people. All right, how many ways to get to P1? P1 is equal to S plus P2. Because, yeah, a path that lands here is going to get from here to there. All right, P2 is P1 plus 3, P3. All right, what is P3? You might think it's P2 plus E, but it's actually just P2 because no path will come from E. Once we go to E, we stay there. So let's go and see what happens. Is it symmetric? No. That's what makes this bash necessary. This is 0, this is 1, this is 0, this is 0, this is 1, this is 0. All right. So now how many paths can go to S? P1 plus P5 is 0. P3 is P1 plus P3. Where did I say that? All right, so S is going to be P1 plus P5, which is 0 here. And that sort of makes sense. And then we could sort of do this sort of like branching thing. That's, okay, this is why I'm putting these all in quotation marks. This is really bad notation. What this means is that P3 at like a certain time is going to be equal to P2 from the previous time. So time t minus 1. I'll write that here. This is my bad because I'm using horrible notation. Oh, I'm already over. I hope my research mentor doesn't get too mad at me. And the reason that like I do this is because now we can do this whole like sort of branching arguments. These two are going to add to get this value. You're going to add to get this value. There's one way to get to P3. No ways. Oh, one way to get to E. P4. How many ways are there to get here? 0 plus, or just 0. All right, and P5, 3 ways. So I think at this next stage is where the symmetry starts to break. So P1 is 3, P5 is 3. So S is 6. P1 is now 0. P2 is now 4. What is P3? It's actually 0 because it's equal to the P2 of the previous one. E. Oh, and E is also going to equal P3 plus itself plus P4. So this is going to be 2. This is going to be 3. This is going to be 0. To check ourselves, we can make sure that the sums of each column, excluding this S in the bottom, because that's just copied, is equal to 4, is equal to a power of 2. So the sum of this is 2. Isn't this extremely bashy? It is. But I'm already like a third of the way done with it, and it hasn't even been 5 minutes. This is an AME 14. You're meant to have a lot of time for these last problems. What do these sum to? 2 plus 1 plus 1 is 4. 3 plus 1 plus 1 plus 3 is 8. 6 plus 4 is 10, 12, 15. Huh. Must have missed something. Yeah, so you see that I've already caught an error. Because P4 is... Huh. Oh. Lots of places to add it wrong. Yeah. Is there any better way to do it? I think this is the cleanest, and that's saying something. Okay. The thing that I said about checking if like the sums were a power of 2, that is wrong. Because things start to break. S is equal to 0, I think. Because S cannot just like stay at itself. So 0 plus 0. There are no ways to reach S here. P1 is 6 plus 4. P2 is 0 plus 0. P3 is 4. And now this is important because we're not... E is going to be 0 plus 2 plus 3, which is 5. P4 is going to be 0. P5 is going to be 9. And this is, of course, going to be 0. So then we can continue. All right, 10 plus 9, that's 19. 19 at the top and bottom. P1 is 0. P2 is 14. P3 is 0. All right, it's P4. 4 plus 5 plus 0 is 9. P4 is 14. No, just 9. Yeah, that's tricky. P5 is 0. And you might notice that there's a sort of like alternating 0 thing going on here. You can also use this to help simplify your work. But yeah, I do not know of a better way to do this, but I just want to show that this is a valid way of solving problems, and it will lead to a correct answer. I actually got this right, which is quite amazing considering that I actually make sillies like crazy. But you see this method of just sort of a recursive idea, using the previous row to generate the next state, and just keep on going on. When you're doing this, your minds work faster than my mouth. You'd be surprised by how quickly it would happen. All right, I think that's everything I want to cover. So are there any other questions? Well, I had to leave right now, so I can't answer them, but you can definitely direct them to Andrew. So yeah. I'm gonna see if he has to answer any last minute questions. I will transfer meeting ownership to him, and then bye.
All right, if you have any questions, just let me know real quick. I'm going to end the meeting soon in like the next 2-3 minutes. So just let me know. You feel free to leave. Justin has to go. So yeah, see y'all again. If you have any questions, just let me know right now real quick. Anyone? I'll wait another minute, and then if no one asks any questions, I'll end the meeting. All right, thanks. Yeah, so I'm gonna end the meeting now. Seems like nobody has any questions, so have a nice day. See y'all. And our next meeting will be this Friday in 2 days, so feel free to come.